Thank you. So we're going to be discussing how to combine the structural and functional connectivity, some of the methods that are available. And there is no need to talk to this audience. We saw a lot that diffusion MRI is very powerful to look at the structural connectivity, but also MRI has bold, base, on ASL and other methods to look at functional connectivity. And while the structural is looking at the cabling of the brain, the functional is looking at the neural synchronization between different areas of the brain. So, for example, in this study, if we look at area orange and yellow, you can see that the functional data is synchronous with each other. For example, in those two areas are then considered to be part of a functional network. And it's believed now that functional connectivity is facilitated by structural connectivity, and there are, to some degree, a correspondence between the two, and also has been well accepted now that plays an important role. And this is, for example, for the study by Chris Honey, where they were doing parcellating the brain, the cortical regions, and then looking at the structural connectivity between the links in the structural and the links in the functional connectivity. And they found there was a good correlation, but at least when you were considering the links, the edges, that they had a structural connectivity. So they were restricting this analysis for that. When you included all the links, this correlation decreased. And similarly, what they found is if you were doing a test-retest study in the functional connectivity, and you plotted the functional connectivity of the first study in the X and the functional connectivity in the second study in the Y, and again, in black are just the links where there is a structural connectivity, what they found that it was much more reproducible. Those edges were much more reproducible in functional connectivity. So to some extent, functional connectivity was more reliable when there was an associated structural connectivity link. So the overall thing was that structural connectivity plays an important role. But as mentioned also before, it is not the whole story. So the relationship is far, far from imperfect. You know, there is the indirect connections wherever we have two nodes. Functional connectivity may be talking to each other there, but not through a direct path. Could be through an indirect path through a third node or a fourth node. And also the functional connectivity, the dynamics are very important. You know, things change in an order of minutes very, very quickly. Well, obviously, we don't expect changes in structural connectivity in that time scale. And a nice analogy that was recently I've seen in a recent paper was to kind of relate the connectome with a road system. And you know, it's obvious that they were making the analogy of functional connectivity is the traffic volume, the structural connectivity is the size of the street, and it's obvious that the size of the street, the larger the street, the easier it is for volume, the traffic to go through that street. But in the short time scale, the dynamics of the population plays an important role. So I'm sure any of you have had trouble with rush hour at some point. And for example, these two streets have both 3 lanes, the same size, but it's likely, for example, in the morning, there will be high traffic on one way, and in the afternoon, high traffic on the other way. So it's not, it plays a huge role, but it's not the whole story, obviously. Typically, these things have been studied, this connectivity have been studied separately. But there is a lot of interest in the last few years to how to combine them together to leverage one information from the other. The way that this has been done, the first one would be just the simpler one, that is just do each analysis independent from each other, and once you get your results, put them back together at the end, either qualitatively or quantitatively. But there are other ways that we can do this in a more informative way. So, for example, we can use one modality to inform the other. And then, for example, this is just one particular way. For example, it's taking the functional connectivity results to guide the structural connectivity. You can take the functional connectivity results as seed and target for fiber tracking, for example. And we can see here an example. What they did is they did bold fMRI, and they defined this functional network. In particular, this is the default mode network. And then they took some of these nodes at seed and target to look at the connectivity, the structural connectivity. So, for example, they have this one, the medial prefrontal cortex, the posterior cingulate cortex, and the retrosemial cortex, and then here the medial temporal lobe regions. And then they use them as seed and target, and then they study the connections, and they saw, for example, that this connection between these two nodes was more rostral than the connections between the temporal lobe and things like that. We can do the opposite way around, so use the structural connectivity results to guide the functional connectivity, and this was nicely illustrated by the group from Maxime de Cateau. What they were doing is illustrating this figure. So they took a seed region, shown here by the blue arrow, in the cingulum. Then they did tracking, generated the cingulum bundle. Then they went to the endpoints of the track at all these red areas. And then from that one, you can calculate the mean of the ball signal for that subject. And then you use that time course to correlate with everywhere else in the brain and find your functional connectivity area shown here by the red region. So they find a functional connectivity in the network guided by whatever the tracking that you had. So in this case, it was a cingulum. It's a key node of the pathway of the default mode network, and that's how they managed to reconstruct the whole default network from this. Another way that we can use it to one inform the other is to do some modeling of functional connectivity based on the structural connectivity results. And this, again, is from the work from Chris Honey. Schematically, what they did is they took a whole brain tracking, a given cortical parcellation, and then they generated connectivity matrix. So each node here is how structurally connected is one node to the other. And then they did some modeling. And there are various ways to do this, but the most common one that people use is some kind of neural mass model, and then subsequently with a balloon model to model the ball signal. And in that way, what you can generate is, with this modeling, this structural connectivity, what function connectivity should give you. But obviously, what you can also do is acquire ball data in those same subjects, use the same parcellation, and calculate the actual measure of functional connectivity data, and then relay one to the other. And what they found is that they correlate the measured data versus the simulated data. There was a fairly good correlation, again, just considering the edges where there was a structural connectivity link. And having a modeling has advantage. Once you have a model, you can start playing on changing parameters in the model and predictions and things like that. It's a very active field, this one of modeling functional connectivity based on structural connectivity. The ones that I'm going to focus for the remaining of the talk is the ones that actually you do the analysis joined together. So combining the very earliest stage in the analysis, and then in some way you're trying to integrate information that is available a bit better, or more comprehensive. So one of these type of approaches is using blind data-driven approaches, and it's been pushed by, for example, by the group by Vince Callon. They did quite a lot of work. They're doing quite a lot of work on this. And for example, this is just for one of their methods. This is multimodal canonical correlation analysis, followed by a joint ICA, independent component analysis. And it's schematically shown here. For example, you take your fMRI data in your controls and patients, the group, and your DTI data in this case. And then, for example, for the fMRI data, you took a particular feature. You need to use a kind of a scalar value for this. And they, for example, they use the results from a standard fMRI analysis, the networks that you will find from a standard fMRI analysis. For the diffusion, again, you need a feature. They were using DTI features. In this case, fractional isotropy. They use radial diffusivity and other features too. And then you take these two features and you do a multimodal canonical correlation analysis, each one with its mixing matrix, and you generate your components for the MCCA analysis. And then you take these two components, you concatenate in them, and then you do a subsequent joint ICA to separate them, and then you keep pairs of independent components associated to each other, one spatial, one functional, one structural. And just to illustrate one of these ones, for example, this is on the left, this is component number 9. On the left is for the functional data. This was, if I remember right, were patients with schizophrenia and bipolar disorders, and it was an auditory task. And these are the networks for that component. And the associated structural component from fractional isotropy was this one here. And then they can go over to, for example, start creating, based on the regions and the pathways involved, try to generate some high-level network pathways to explain these differences with these pathologies. One of the disadvantages of this is, compared to the other ones I'm going to show the rest of the talk, is that it doesn't use whole brain tracking. So in some ways, a limited amount of information related to structural connectivity, but it's still very useful information you can connect between these two modalities. So another of these methods, known as activated fibers, what it does is associate dynamic functional connectivity to each streamline in your tractogram, and then you do a standard fMRI type of GLM analysis to find what areas are activated. So to look at this in a bit more detail, and we look at the flow graph in the paper. So if you look at the top part, is kind of the standard fMRI thing. You take an fMRI task kind of activation, you get your fMRI data, you put into some kind of a GLM analysis, for example, and you get your network of activation. What they were doing is then taking a whole tractogram and each of these streamlines at a time, finding the endpoints of the streamlines, and from the ball data from those endpoints, associated to that streamline a dynamic functional connectivity value. So now each streamline, you can treat it as kind of a pseudo-voxel, and then you can put them into a kind of a virtual image, and then feed it through the same GLM method and find which area of activations are lighting up. And in this case, the voxels correspond to fibers, so you can map them back to which fibers in the brain are the ones that they are activated. And for example, for this one was a work memory paradigm that we're using, and they found which fibers were the ones that they were activating with this approach. And then they can do is map this back to which areas in the gray matter. So for example, for this same activation, this map was the one you get with the standard fMR analysis looking at the ball data. This one was the one that they were getting from their activated fibers approach, and that's the overlap. And then they discussed there in the paper that one kind of including the other, and if that implies that it's more sensitive and things like that. But it's a way, again, to try to use the two information together, one to inform the other. Another way people have done it is this method known as anatomically weighted functional connectivity. And this is essentially you're trying to define a new functional kind of weight the functional connectivity with the structural information. Schematically, how it works is they get the ball data. From the ball data, you can generate a connectivity matrix. So each voxel here is each entry here is the connectivity between two regions. Then you take your diffusion data, your tractogram, and you generate the structural connectivity matrix. And then from these two, you can generate a weighted version of the one here at the top, weighted by this one. In their particular ways, they took the functional connectivity and they weighted it by this structural connectivity. So a big parameter of lambda would mean not much influence from the structural connectivity. A low parameter of lambda would mean it is very influential. And they had in the paper some suggestions how to optimize this lambda. So now you have a new matrix that you can use for your standard graph theory, but these metrics have both information from structure and function together. Another way that one can do, and could be considered if you're in some way is an extension of that one, is to go to a full Bayesian framework. So if you take now the structural connectivity information as a prior in your functional connectivity, and you study your functional connectivity in a Bayesian way, you're using that information to help inform the other. And there are several studies that have done this. This is just a couple of the references. And if we look, for example, at the last one was a very recent study, the kind of results that they found, for example, they're showing here the mean positive rate, so the higher the better. And then the red one is your standard bold analysis that you will get doing functional connectivity in isolation. And this one here is the one where you use the structural connectivity as a prior. And what they were showing is that if you reduce the data size, the Bayesian framework was much more robust, because in this case you don't have the gold standard. So they were using this criteria to say more robustness to data decimation suggests that the analysis method is more robust. So again, it's using structural and functional information to inform each other in some way. Another method that is becoming very, very popular in recent years is using multi-layer networks. And this is when you have different layers to describe different strength of interaction, different edges. So to explain this a bit more, this is illustrated here. So let's say you have, in this particular, 3 layers. In our case, we're only interested in 2 layers, structure and function, but it's being used a lot, for example, for temporal dynamics. So you're looking at different layers for different time points, or different layers for different frequency bounds when you're looking at ball data and things like that. So in general, let's say you have 3 layers and a given network that you're looking. So each of those layers will have a connectivity matrix, as you can see here, telling you how, within that layer, how things are connected. But also what you can do is condense all this information into what is known as a super-adjacency matrix, where all the things you're using the extra information that each of these, let's say node 1 is connected to node 1 in another layer and connected to node 1 in another layer. There is a labeling that you know that they are linked to each other. So if you look at this matrix at the diagonal blocks are pretty much the same as these ones, are the same as this one. So it tells you the intra-layer information, and the off-diagonal blocks tells you the intra-layer, the diagonal, and the off-diagonal, the inter-layer. So for example, 1 in layer 1 is connected to 1, and layer 2 and 1 layer 3. And there are ways that you can do, typically this can be done by putting ones everywhere, or you can use a priori information on what to assign these values, or you can even optimize it based on some parameter optimization. So as I said, this is a very strong method to look at different modalities and then look at the interaction between the different modalities. And a recent study, for example, that used this type of approach, they were using diffusion, in this case DTI, for their connectivity, ball data for their functional connectivity, and they had the 2 layers, one for the functional connectivity, where you have 3 options, so positive correlation, anti-correlation, or no link at all. And for the structural layer, they had a binary approach, so they were either a link was present or a link was absent. And they were looking at, in this paper, at motifs, that there's small subgraphs that they are overrepresented within a network. So for example, for a simpler case of a 2-node motifs, you have all these are all the possible combinations. So, both present and function structural, anti-correlation and present structural, no function but structural, and so on. And they look at how the statistical distribution of these things. And for example, they found that the one where both are present is the one that is most represented in the system, in the data. While the one, for example, that is least represented is the one where functional connectivity is present, but structural connectivity is not. Again, suggesting the importance of structural connectivity to functional connectivity. And then in that paper, they look also at 3-node motifs and other more complex ones. So the approach that we developed in our lab, and for the one I'm going to talk for the rest of this talk, is based on the track-weighted imaging framework. This is just a general framework where you can take a tractogram from diffusion MRI and any images that you want and combine them to generate a track-weighted version of the one that you're using. So if you want, for the particular case of mixing structural and functional connectivity, it's just one specific case of this one, that is where the image that you're using is just the functional connectivity data or the ball data, for example. So to explain this in a bit more detail, if you take your diffusion MRI data, you can generate your tractogram. If you take your ball data or any other fMRI data you use, you can generate networks, either functional connectivity, fMRI, or any other network that you generate. And then you can combine them to generate track-weighted version of the network that you had here. And this is where the method kind of branches into 2 main ways to do it. One is where you have a specific network, and that's the one I just described, and I'll show some examples in the next few slides. And then the other one is where you don't, so that's the one I was saying, and the other one is where you don't have a network. We get rid of this intermediate step here, and yes, we go from the whole ball data, combine the whole ball data with the whole diffusion MRI data into the track-weighted data. So if I get to the first example, the one that you do need a network to define which network is the one you're interested in, and I'm showing here for the case of functional connectivity. So let's say that we're interested in a default network. It's shown here for ball data. What you can do is then take in this subject the same data for diffusion MRI, generate your tractogram, and then go streamline by streamline, look at each of them at a time. So for example, let's say that this is the streamline we're looking now, one of the streamlines in the cingulum here. And then you assign to that streamline a given amount of functional connectivity. And there are many ways to do this. The simplest one probably is just to sum the functional connectivity values of your network here. So things that are streamlines that go to the hotter areas or to many of these areas, then they would have high values. Things that they are not part of the network would have low values. You do that for every single streamline in your tractogram. So each of them now would have an assignated value of how much connectivity they are associated with. Then you overlay a grid, and on each of these grid element voxels, you go and average all the values that you have for those streamlines. So let's say you have 50 streamlines, each with given weighted functional connectivity. You go there and calculate the mean of those 50 streamlines, and you assign that value. And then this is, for example, the kind of results that you would get. Just to remind you, so this was the default network, and you get an image that is like that. So to some extent, you can see what it's doing is taking the information of the functional connectivity and using the fiber tracking to propagate information. So it tells you in some way what structural information is involved in this network, but still the intensity is related to the functional connectivity values. As I showed that in functional connectivity, but it obviously can be done with any network. You just had to define a network. So for example, this is using a language paradigm, and you get your language fMRI network. You mix it with your structural connectivity, with your tractogram, to generate, again, here you can see the aqueous fasciculus connecting Broca's and Wernicke's area. And again, so the structural connectivity is given by that one, and the intensity is given by that one. It's propagating information of that one through the networks of the structural connectivity. This is another example. So this is a patient with epilepsy with cortical dysplasia. You take EEG fMRI, you find your network, and you use structural connectivity to relate what is the structural underlying that network. How is this network talking to each other? This was just briefly to mention that all these results I'm showing here are for scalar maps, but you can still obviously keep the orientational information within the results. So for example, if we take that same example I was showing, you take your language network, your tractogram, you can generate now that this track weighted, but instead of a scalar value at each voxel, if I zoom here, you can maintain each of these lobes or directions within your method uses spherical deconvolution or any other method, QBall or whatever you use, and maintain the track weighted in each of them separately. So you can see, for example, here, I don't know, this bundle here has high track weighted, that one has low track weighted. So the ones I was showing before was just the average of these two is just condensing this into scalar. The disadvantage of this one is that obviously it's much more complex to visualize and it's not as easy to deal with, but it has big advantages. So you increase the specificity, you're not mixing now the information of bundles, you're keeping them separately. And in particular, if you're going to do any quantitative analysis, you can use enhance the statistics with the connectivity-based enhancement that was developed for the apparent fiber density and the variance of apparent fiber density. So the second version of this one, and that's the last one I'm going to show, is the one where you don't need to specify the network. You use the ball data itself. And this is illustrated here. So if you take, let's say we're looking at this voxel here in the brain, you would go and look at all the streamlines that go through that voxel. Let's say schematically, this is one of the streamlines. You go to the endpoints of these streamlines and get the ball data from those time courses. And then as the other method, you assign to that streamline, essentially you're mapping the ball data to the white matter pathways. And in this case, what we use is the correlation between these two time courses, the cross correlation. And you can see it do it even in dynamic framework, taking a sliding window approach and just doing this in the correlation in a sliding window. So this weighting that you're assigning is actually time-dependent weighting. You do that for all the streamlines. There are 4 here, but obviously there would be many more. And then the final value is the average of those weighting. And that's what we call here track-weighted dynamic functional connectivity. And just for comparison, I'll be showing you the same thing, but without a sliding window, just taking one whole data set and correlating to each other. So they're the same, but for the extreme case where the sliding window is infinity. So how do they look in practice, this data? So if we're looking at an axial slice here to the basic ganglia, that would be the track-weighted static version without the sliding window, correlation units. And this is the dynamic version in that case with 1 minute sliding window, again in dynamic things. And you can see how things change a lot. For example, if you look at the fornix, it's changing the correlation, this amount of synchronicity between the areas that are connected through the cingulum. So the fornix changes a lot. The optic radiation is going to see also here changes. Things in the thalamus are changing also quite a lot. Another way how we can visualize this is going to the gray matter, white matter surface. And if we look at here, again, we're looking at the changes in synchronization. We're looking at a subject from the back, from up on the back here. And you can see, again, if you're familiar with networks, you can see the nodes that appear are things in the visual cortex, sensory motor, part of nodes of the full network, temporal areas, cerebellum areas. So these are areas that are becoming synchronous and disappearing during the sliding window approach. So we can look at these dynamics in many ways. Possibly the simplest one would be just to look at each voxel, see how this change is happening, calculate the 95 confidence interval, and calculate a map. So this would tell you red areas here would be things that are changing a lot, blue areas are things that are not changing much. So for example, the fornix, as we were saying, is changing quite a lot. The cingulum bundles here going in and out of the plane, changing quite a lot. Optic radiations, ventrolateral nucleus of the thalamus is changing quite a lot. And then some areas like tapetum, some of the corpus callosum structures are not changing quite a lot in the way how the synchronization between the gray matter regions that they connect are changing. So now what we have is a 4-dimensional data set that has both structural and functional connectivity information there. We can put it through many analysis, and in particular, we can do the same analysis that we do for your standard fMRI data. For example, you can put this now through an ICA. Take these 4 data sets and put into an independent component analysis, and you would get a set of components. I think in this one was something like 60 components that you get for the data sets that we had. This is just a couple of these components. Each component would have obviously a spatial map and a temporal course. And for example, in this one, you see is the one that is primarily the cingulum, connecting the posterior cingular cortex with the medial prefrontal cortex. And the time course that you would have for that component is related to the synchronization, the temporal variation and synchronization between those gray matter regions. Here in another of the components, the optic radiation connected the lateral genicular nucleus with the primary visual cortex. And again, the changes that we see will be related to the connectivity, synchronization between those two regions. So you can use this to look at temporal dynamics and how things change in the brain. But also there is a lot of huge amount of information in this one. And for example, we can use it for parcellation. And this is illustrated here for looking at the mid-sagittal corpus callosum. So if you take the mid-sagittal corpus callosum and you take all your components, as I say, I think there are about 60 or so for the data we had, and you threshold those components, a given intensity for a given cluster size, and this is what you get, for example, for a single subject, and this is what you would get for a group of 8 subjects. So you can see that now, based on the connectivity, structure and functional connectivity, without imposing constraints about the cortical parcellation, you can start parcellating the white matter structures, and the results are similar to the ones that you get by having to impose those constraints. And even now that we have the white matter parcellation, you can take your white matter parcellation, do your standard tract editing, and also then lead to a cortical parcellation. So for example, we can take each of these regions at a time. Let's take this one here, take your tractogram and tract edit, so only isolate the ones that go through that region and assign those ones to that region and do that to all the other ones the same, and you get something like this. So based on the structural and functional connectivity, including dynamics, you can start parcellating the transcolossal connectivity in a data-driven way. So as a discussion, these 2 methods that I showed at the end, the track-weighted functional connectivity and track-weighted dynamic functional connectivity, allows you to combine structure and functional connectivity so do the analysis in a joint way from earlier in the analysis. The first one I showed, the track-weighted functional connectivity, is a static version, so it only uses a 3D image, in particular the one I showed, and it helps you highlight the white matter connections involved with your network. But still the intensities are related to the functional connectivity. And it can be done for any functional network, but you need to specify which network is the one you're interested in. The second method is the dynamic functional connectivity. It's a 4-dimensional data set, so you can use it for studying dynamics. It's more general in the sense that you don't have to specify networks, you look at the whole data at the same time. And the key difference compared to other methods that look at dynamic functional connectivity is that we are operating in white matter. So whenever you see a change in white matter, that change relates to the gray matter region that pathway is connecting to. And it helps constrain a very large amount of data. If you were to do this directly in the ball data, you would need to consider the connectivity between every voxel to every other voxel in the brain, which is it's a huge dimensional. So we're looking at the direct connections. For the more general thing, as I said, there are many ways to do, and I would say that it's a huge field at the moment how to combine them. You can use them independently and combine them at the end. One informs the other or in a joint analysis. Each of them has advantages and disadvantages, so that, some are simpler to do, simpler to analyze. The other one requires more involved methods. But I would say the joint analysis provides better integration. Regardless, any of these methods, the ultimate aim is to provide further our understanding of brain networks, or provide biomarkers if you want to study a particular disease or cognitive process or something, a biomarker for that. The work I presented here obviously is not just my work, it's all these people have been heavily involved in this. And if you're interested in work in Australia, just send me an email. And that's it. Thanks.